Hello everyone, this is Xinhao, a PhD student from Center for Visual Speech and Signal Processing at the University of Surrey. I'm going to present our paper Audio Captioning Transformer for DCASE Workshop 2021. The co-authors are Xubo, Qiushi, Huang, Mark Plumbley, and Wenwu Wang. This talk contains 5 parts. I will introduce the audio captioning task at first, and then talk about the existing methods, and present our proposed method in the third part, and talk about the experiments in fourth part, and draw conclusion at last. Automatic audio captioning is a cross-modal translation task which aims at generating a natural language description for a given audio clip. That is, the AAC system receives an audio clip as input and outputs a natural language description for the given audio clip. Compared to audio tagging and sound event detection, AAC requires detecting the audio events and their spatial-temporal relationships in audio clip, and also describing the information using natural language. There are a lot of applications such as audio retrieval and assisting hearing impaired. For existing methods, with 2 publicly available datasets, audio captioning and closely released in recent released. Audio captioning has achieved promising improvement in recent years. And this is a novel task. Existing methods almost using deep learning techniques in the following encoder-decoder architecture, where the encoder extracts audio feature and the decoder generates captions based on extracted features. For the model architecture in initial works, RNN is adapted, and the Xinhao was proposed in 2019, and CRNN was proposed in 2020, and the 2 are compared, and the results show CRNN was better than CRNN for this task. And the CRNN transformer was proposed in 2020, and which is a SOTA model now. But the problems for the existing method, we think the CNN can be limited at modeling temporal information for time series signal, especially for audio, and RNN can be limited at modeling non-range dependencies between time frames for non-audio clips. To overcome these problems, we investigated to use transformer for audio captioning. Transformer shows powerful ability at modeling sequence data in NLP tasks. We propose audio captioning transformer, which is a full transformer network without using convolution. This is a diagram of ACT. On the left side is the ACT encoder, on the right side is the ACT decoder. ACT encoder has a better ability to model the global information within an audio clip or in an audio signal, as well as capture temporal relationships between audio events. The ACT model is convolution-free. It's very simple. For the settings of the ACT model, ACT encoder follows the settings in VIT and DIT, which are 2 image classification transformer model, and contains 12 encoder blocks and 12 heads with an embedding dimension of 768. The settings of the decoder will be discussed later. We carry out experiments on audio caps, and we also use audio sets, which is the largest audio image data set. Audio caps is the largest audio captioning data set, which contains more than 50 sound audio clips sourced from audio sets. And for the experiment settings, the batch size is 32. The optimizer we use is add-on, and the learning rate is set to 1e-4. OMAP is used in first 5 epochs. The back augmentation and the smoothing are used. And for the epochs, we pre-train the audio captioning transformer encoder for 20 epochs, and also train the whole model for 30 epochs. Because compared to CNN and the RNN transformer, usually requires more training data to achieve a reasonable performance. So we pre-train the ACT encoder. Then we also utilize the pre-trained transformer model DIT for image classification from computer vision. And this is the reason why we set the settings of the A setting called the same as that for DIT. For audio tagging pre-training, the A setting encoder takes the log mil spectrogram of an audio clip as input and split the mil spectrogram into non-overlapping patches along the time axis. And then the patch sequences are projected into a latent space through a linear layer, and with an append class token at the start of the patch sequence, which is used for classification. And the class token is designed to model the global information of the audio clip. Thus, the class token contains the global information, and this the fine-grained features have a fine-grained information. Because self-attention contains no predation information, such we add the operational embedding into the patch sequences. And the ACD encoder contains the normal layer, multi self-attention layer, and a feed-forward layer. The output of the ACD encoder, we just use a class token for audio tagging, output. And the ACD encoder achieves the mean average precision of 0.43 on the evaluation of audio set, which is close to the SOTA performance achieved by Xinhao in PANS. For the audio captioning training, the whole model is trained using teacher forcing strategy with maximum likelihood estimation. The training objective is to minimize the cross-training load. The load for a single caption is this equation where YT is the ground truth word at the time step T, and the capital T is the length of the caption. Because there is no downsampling layer in the ACT encoder, thus we think the audio features extracted by ACT encoder might be longer than those extracted by Xinhao. This depends on the setting you use in the ACT encoder, the patch, how small the patch is made. We experimented with 3 different variants of decoder architecture: the DCASE, HDM, HDL, which contains a different number of layers in the decoder and a different number of heads, but all the embedded dimension is 512. Here are the results. If we look at this one, if we just train the ACDM from scratch, its performance is the worst, even compared with the Xinhao transformer trained from scratch. It's really worse than the Xinhao transformer. This proves that the transformer needs more training data than Xinhao. And even we just use a pre-trained DIT, an image classification model, its performance improved from 0.314 to 0.367. It improves a lot. Its performance improves a lot. And then if we further pre-train the ACD encoder on audio set, its performance improves a lot. Improved to 0.413 for ACTM, and for ACDL, it can achieve the spider of 0.420. But these 3 different decoders achieve very close for performance, and not the deeper Wang achieves the best performance, although it achieves the highest spider, but the other metrics are lower than the shallow ones. And overall, compared to the Xinhao and Xinhao transformer models, we can say SAT model achieved higher scores in terms of Blue 2, Blue 3, and Blue 4 and row JL. And also SAT model achieved close performance to SOTA linear transformer model. This shows that our proposed SAT model is effective, even though it's simple. So for the conclusion, we proposed a lower full transformer network audio captioning transformer for audio captioning, which is based on attention mechanism, and the linear layer is very simple but efficient and shows competitive performance compared to other SOTA approaches. But to achieve a reasonable performance, we also show that SAT requires encoder pre-training. The transformer-based network requires more training data than CNN. However, SAT now just works well on audio caps with 10-signal audio clips. Future works should be carried out to adapt it for audio with variable lengths. Thank you for listening.